Today we're looking at things that affect differentiability. Now that means things that will affect the ability of a function to be differentiated so that we can find the gradient of a tangent at a certain place. Now there's a few things that can cause problems with a function being differentiated. The main ones are we're looking for any place that there's a gap or where our function is not actually continuous. And the reason this makes sense is because remember our very definition of the gradient of a tangent to a curve. If we're finding a tangent at, say, P, then our entire definition of that tangent and the way we find it is we find a secant, PQ, and then we make Q slide closer and closer to P until it's so close that it may as well be right on top of P. And at that point we say that the secant PQ is justifiably, basically, a tangent at P. So what that requires is a certain consistency in our function. We need our function to move along predictably. And if it's not predictably moving, then we can't slide that Q closer to P and be really confident that it's going to keep following the rule that the function embodies. So we're looking for graphs that are continuous. Now, there are a few things that can make a graph not be continuous. If we have a vertical asymptote, then we're going to have a value of x where there is no part in the graph. So think about something like maybe a graph of y equals 1 over x, which looks something like this. Now we know it has a vertical asymptote and a horizontal asymptote that sit right on the x and y axes. But if we're looking to differentiate this thing and we're differentiating y with respect to x, then we're looking at the gradient of the curve in all of the values of x. Now, the horizontal asymptote doesn't really get in our way of finding what the gradient is in any place on these curves, but the vertical asymptote does, because we know that this graph doesn't actually go through the y-axis. So we can't differentiate this function when x equals 0 because there's an asymptote there. The presence of a horizontal asymptote doesn't really affect us in this situation. So we're looking for vertical asymptotes because when we find them, we know that we can't differentiate the function at those values of x. We're also looking for other reasons that might cause gaps, and piecewise functions frequently have gaps in them. We'll look at those in a moment. Now, other things that can stop a function being differentiable or differentiable is finding areas where it's not smooth. Now, by smooth we mean we want consistent and following the function at all times. So we don't want sharp corners. If we have sharp corners, we can't differentiate. Now, we sometimes see those sharp corners in piecewise functions. Once again, piecewise functions can stop us differentiating a function for two reasons. They may or may not have a gap, and they may or may not have a sharp corner. So we'll look at those in detail in a moment. Absolute value functions, we've already seen what they look like. If we have a function like this, we know that it has a gradient of 1 over here and a gradient of -1 over here, but we can't differentiate it right on that point because there's not a smooth interplay between the two. So how do we check if there is a smooth interplay? Well, there's a way that we do this. The way that we test for it is we actually just check f dash x on either side of any sharp area, potential sharp point, and if it's actually the same on both sides, then we know that we don't really have a sharp corner. So we're not just going to look at it and say, oh, is it sharp or not? We're going to actually do a mathematical test on it, and I'll show you that in a moment with a piecewise function. Now, other reasons we might not be able to differentiate, well, you can't differentiate a section of the graph that is vertical. And that's because here the gradient is actually undefined. Rise over run, the run is 0. So we really can't differentiate that. We also clearly can't differentiate parts of a graph where the graph doesn't exist. So, I mean, we can see an example of both of these. Let's just make a bit of room on the board. I'll just rub this out for now. If you look at a function like, say, this, which we know is a semicircle that goes from 2 to -2 and up like that, then if we look to differentiate this thing, think about what's going to happen. The first thing that we'd need to do is we would need to rewrite it. Instead of with a square root, we would probably put it to the power of a half. And then to find dy dx, we would need to follow the chain rule. We'd bring our half down the front. we'd have to bring out minus 2x from inside the brackets to come out the front. So half of minus 2x is just minus x. And then we'd have to write all of this again, but instead of to the power of half, it would be to the power of minus a half. Now, to the power of minus a half means all of this would be on the bottom of a fraction and in a square root sign. So I could actually rewrite it that way. I have my minus x on the top, and on the bottom I have 4 minus x squared, all in the square root. Now you can see clearly there that as soon as x is bigger than 2, or smaller than minus 2, we're going to get a negative number inside our square root bracket, which we can't calculate. So obviously the graph doesn't go out here or out here, so you're not going to be able to differentiate it there. But even more than that, we can't actually even differentiate it when x is 2. Why not? Well, when x is 2 or minus 2, on the bottom of this fraction here that tells us what the gradient will be, we have 4 minus 4, which is 0. And as soon as we've got 0 on the bottom of a fraction, we know that we've got a gradient that's undefined. So that means that this graph is only differentiable when x is between 2 and negative 2, but not equal to 2 or negative 2.